Hey y'all, so as I promised, I'm finally getting to this video about proof by mathematical induction. So we're gonna kind of be looking at another type of proof. I like to think of it as if we can prove one thing and then the next value of that, we can kind of prove it for any single case. So it's kind of something as simple as saying if we have a value x, we know that the value x plus 1 will always be greater than this. So something as simple as this, it's pretty straightforward. We can do some examples. We can say, all right, well, for example, if x equals 0, our statement is 0 is less than 1. So notice here, no matter what number we put in, we're always going to get a true statement. So for this one, it's pretty straightforward, but sometimes we're going to have rules, we're going to have theorems where we actually have some not so obvious methods being put into place. So for this, we learn how to do this proof by mathematical induction. And this proof really has two parts to it. Our first part that we always want to kind of try to show is that the first case is true. So say we have some value k equals begin. So in this case, our starting point can be any number because it works for any number, but maybe we start off at the value of 1 and say, okay, we want to prove that 1 is less than 1 plus 1. Well, we simplify that to 1 is less than 2, we've got our true statement. So we show that k equals begin is true. And once we have that starting point, we can actually expand this out and say, all right, well, step 2, we want to show that if our assumption p of k is true, then somehow we have to prove that the k plus 1 term is true. So we kind of did our example of showing that our beginning value, say it's 0, so we could say for x equals 0, 1, 2, etc., x is equal to 0. Another way we could show this is by saying, all right, well, if we know x is less than x plus 1, we can assume that that thing is true. So the big thing that we need to keep in mind is that there is always an assumption. In the case of our original example, it's saying that x is less than x plus 1. We're holding that to be true every single time. So if that's true, then we want to show that when we replace our x with x plus 1 or look at the term afterwards, we actually get a true statement there. So we can look at this and plug in an x plus 1 for every time we have x. And we'll actually get that x plus 1 is less than x plus 1 plus 1. So here if we simplify both sides, we're going to see, all right, we can add 1. We have our assumption right here. And we're saying, all right, if we add 1 to x on the x side, then if we add 1 to the x itself, it's still going to be greater than 1. So in this case, our proof is super duper straightforward, but we actually are going to be able to use it, the same sort of reasoning, to talk about more difficult proofs. So I got 2 more for y'all. I'll see how long this takes, maybe 10 minutes for each proof. But I really want you to know that the heart of this is showing that the beginning one is true, that we have 0 for this one is less than 1, so that's true. So if we can assume that this part is true, then we can test it with the value after it. So we could have x equal to 5, and then if we prove 6 is right, if we have 7, we can prove 8 is right. By making this general, we've proven that if 1 is right, value is right, the value above it is also true, and therefore every single value is true. So let's start off with our first example. In this example, we're going to say, or we're going to try to prove that k squared is greater than k plus 1, okay? And we're going to do this for all values from from 2 greater. So any value 2 and any value greater than that. So we see that this actually wouldn't be true for 1. 1 squared is just 1. That is not greater than 1 plus 1. So that's kind of why we restrict it to starting at 2. So our first thing we want to do is prove that our proof here, right here, evaluated at 2 is going to be true. So the one little thing that always gets caught up here is nobody knows what the assumption is, and you're always having difficulty figuring that out. The assumption is always what they give you, okay? So we're just going to use this assumption and plug in a value of 2 for it. So we're going to prove that P of 2 is true. P of 2 is true. So we just plug those values in. We get 2 squared is greater than 2 plus 1. And when we simplify this, we actually get that 4 is greater than 3. So I hope at this point you realize, hey, that's a true statement. If you get to a point like this and it's not a true statement, then you can't even do the method of mathematical induction. So the easy part's done. Now we move on to a part that's a little bit more difficult, and we actually need to be very mindful about how we approach this. Some people like to go to the end point, meet halfway in the middle after starting the proof. This is one where I actually find it's relatively straightforward once you've actually seen the proof to see the flow of logic. So I'm just going to go for it one step at a time. So the first thing we need to do is assume P of k is true. So here our assumption is that k squared is greater than k plus 1. And this is going to be crucial because we're actually going to use this inequality to make more inequalities farther down the line. So our next thing we want to do is show that P sub k is true. Show, oops, that was a little too dark. Let's try to get a lighter blue going here. Oh, I wonder if this one will work. My students were using these Sharpies, so some of them it's hit or miss. They love coloring with these things. So we're going to show, okay, this one will work, that P of k plus 1 is true. So what this means is that every time we see a k in our assumption, we're going to replace it with a k plus 1. Okay? So we have that k plus 1 squared is greater than k plus 1 plus 1. So notice here, every time I had a k, I replaced it with k plus 1, here and here. So what I'm going to do now is actually look at our two sides. So I'm going to make this a little bit different colors, okay? What we're going to do is have a focus side and a different side. So this side is going to be k squared plus 2k plus 1. And we're going to assume that this is actually bigger than k plus 1 plus 1. But I want to focus, I want to focus on this green side right here. I want to look inside and see, hey, I have a k squared. So if k squared plus 2k plus 1 is one of my values, and I know that k squared in itself is greater than our assumption, k plus 1, like so. Then if I add 2k plus 1 to both sides, that inequality should still hold because I'm adding the same values to two sides. Doesn't matter what k is, we're always adding 2 times that plus 1 to both sides. So I'm actually going to do that right here as well. Okay. So, oops, plus 2k plus 1. See, this is a little tricky. So basically what I did, I'm ignoring this right side for a second. I'm comparing my left side to the actual assumption I'm making with this update that I'm going to add 2k plus 1 to both of these sides. So I took my assumption, I added 2k plus 1 to both sides. So from there, what we can do is actually simplify this left side. This is just saying k squared plus 2k plus 1 is going to be greater than 3k plus 2, okay? But now let's look at what our p of k plus 1 is saying. It's saying if k plus 1 squared is greater than k plus 1 plus 1, or just putting it back into here, then we can also show that by a transitive property, if we can show that the green side is bigger than our assumption, then in that case, it'll actually be bigger than what we're trying to prove in the beginning. So when we compare this 3k plus 2 now to our value, we'll see that this 3k plus 2 is actually bigger than this original statement right to our right. So we can kind of cut out the middleman here and show that k squared plus 2k plus 1 is actually greater than k plus 1 plus 1, and therefore we have proven our original trait. So this is kind of difficult to see. So I really just want to step through it again now that we've actually gotten to the point. So now by the transitive property, we're going to have k squared plus 2k plus 1 is greater than our original k plus 1 plus 1. And finally, wrapping this all up, we can then factor this back into our squared binomial. And we have shown that this is actually true. So this is kind of a little bit of a check, okay? So what we did here, first thing we did is show that the first value was true, k equals 2. Plugged it in, easy part. Then it got a little tricky. We had to really keep in mind what our assumption was. K squared is greater than k plus 1, and then start exploring the p of k plus 1 case. Replaced our k squared with k plus 1, made that greater, replaced our k with k plus 1, added 1 to it, expanded out the left side, showed it in terms of that same inequality, then said, hey, we don't care about this part anymore. What we want to do now is just zone in on this left part and say, all right, if this is true, and we know that our assumption is k squared is greater than k plus 1, we can actually replace this k squared with k plus 1 squared. And we actually have that greater than part, okay? Oops. I guess not. And so from here we can simplify down to 3k plus 2. That's going to be greater than this guy. Oh, right, because we don't square this part because we're just replacing the k squared with k plus 1, saying that this side is greater than this side. So see how confusing this can get at times. You really have to keep this stuff straight. So from there, we just simplified the right side, showed, hey, if this is greater than this, then this also has to be greater than this. So we expand it back out and show that, to kind of backtrack and show that this is true. So the heart of our proof, the heart of the, hey, we've actually formally proved it, is right here. Okay. That is the point of actually proving it. Okay. So by that we showed, therefore, just a little bit of math notation. Therefore, k plus 1 squared is greater than k plus 1 plus 1. We showed that the first one was true, which was our first step. We showed that if the kth term is true, then the k plus 1th term is also true. So that's our first example. Now that we kind of have this process down, we can kind of work a little, we can go through this proof a little easier. This one's actually one that I find a little bit easier to understand because it's just less equation writing, there's less k plus 1s floating around, all of that. So our next one has to do with looking at sums of consecutive numbers or series and seeing how they're actually equal to a very specific formula. So in your studies way back when in pre-calculus, you might have talked about series saying, okay, if we have a sum from I equals 1 to k of some value I, that's going to be equal to some formula. Well, all this is saying, and this is actually some good review for, let me try to refocus this before we really jump into it. What we're saying right here is like, take your value, start at 1, and then add to that 1 more each time. So 1 plus 2 plus 3, all the way to plus k. So we want to prove that if we have the sum, it's actually equal to the kth term times k plus 1, all divided by 2. So we want to prove this. So we're just going to go through a few examples. First thing we want to find is the first term. Okay, so step 1. Prove p of 1. And you might be wondering, why p of 1? Well, we're starting with the first term right here. This summation notation is telling us start at 1 and go all the way up to k, adding 1 each time, 1, 2, 3, all the way up to our k. So if we're looking at p of 1, well, we got a left side and a right side. Our left side is 1 plus 2 plus 3 all the way to plus k. So if we're looking at the sum from 1 to 1, that's just saying, all right, well, we're at a value of 1. And if we're looking at that value of 1, we want to check to see if it's actually equal to our formula right here. So we've got 1 times 1 plus 1 divided by 2. Or 1 plus 1 is 2, divided by 2, we get 1. So check, we're good to go. Easy stuff done. Now we need to start thinking about, okay, what is our assumption? How can we use that assumption to actually show the k plus 1th term? So our assumption in this case is actually this whole entire statement right here. So 2, assume p of k is true. So right here we've got 1 plus 2 plus 3 plus dot 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 all the way to plus k. That's going to be equal to k times k plus 1 over 2. So this is actually going to be very important in the next step. If we're trying to figure out now that, or show rather, that p of k plus 1 is true, I'm actually going to, this might be a little confusing, but I'm going to try to stay consistent with this and use the same colored marker. So for 3, what we're doing is we got to show that P of k plus 1 is true. Just like in the last example, oops, oh my gosh. So I'm hoping that actually didn't mess it up too much. If it did, it's getting late, so I'm gonna just reiterate what I said right here. P of 1, we found that that's equal to 1. P sub k is true. We got 1 plus 2 plus 3 plus dot 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 plus k is equal to this formula. That's just this overall statement right here. Now we're trying to show that P of k plus 1 is true as well. Now that we finally got that done. If we're trying to show that the k plus 1th term is true, all it's saying is add up to k and then add another term on top of it. So if we're trying to focus it just like we did right here, we're saying all of this plus a k plus 1 term is going to be equal to substituting k plus 1 for k in each of these cases. So we've got k plus 1, that's what we substituted this first group of k with. And then we got to substitute the k and the k plus 1 with k plus 1 in itself. And then divide that whole thing by 2. Okay? So what we're trying to do here is actually show that this side somehow is equal to this side, or that this equality holds true. That's why I was saying this one is a little easier. We don't have to do compound inequalities, try to find a weird middleman that somehow proves the assumption, or proves the k plus 1 with the assumption. All we have to do right here is notice that, hey, we already have this part right here. That is our assumption in itself. So we can actually replace this part with our k times k plus 1 plus over 2. So that's what I'm going to do. K times k plus 1 over 2 plus k plus 1 from right there is actually going to be equal. I'm going to actually highlight this in blue so we know what's what. Is equal to this value right here. So there's 2 ways we can go about this. We can either manipulate the right side to get it to the left side, or we can manipulate the left side to get it to the right side. Since this one is already in fraction form, we'll have to do like fraction decomposition. It becomes this really big, annoying process. So I like to start with the left side. Make the combination of our assumption and the sum be the side where we do all our manipulations. So I'm going to just stay consistent with the magenta and kind of figure out this part. So the first thing I can do is multiply both the top and the bottom of our k plus 1 by 2. So we got k times k plus 1 over 2 plus 2 times k plus 1 over 2. And we know that this is still equal to this stuff on the right side. So now I'm just going to keep focusing on that right side, really figure out what's going on here. So here we have a common denominator, so we can add up these 2 guys from the top. So we got k times k plus 1 plus 2 times k plus 1 all over 2 plus, or whoops, just 2. So this is good news. We have the 2 over it. So now we just need to figure out some way to make this part actually look like the numerator on the right side. So what I should notice here is that I have a k plus 1 in both of these terms. I can actually factor that thing out. So we've got k plus 1. And then we're saying, okay, well, if we divide this one by the term k plus 1, all we're left over with is a k. We do the same thing here, we got a plus 2. We can double check that. I'm going to put this all over 2 just by saying, all right, k plus 1 times k will give us this. K plus 1 times 2 will give us this. Again, still equal to the right side. So now notice we have the k plus 1, we have the 2. Now we just need to figure out some way to split this up. Well, I know I can just turn this 2 into 1 plus 1, group this together, and I've got my proof right there. K plus 1 times the sum of k plus 1 and 1. Well, that's all divided by 2, and look at that, we have exactly what we have here. K plus 1 times sum of k plus 1 and 1 all over 2. Okay, so that's all there is to this proof, and we figured it out. Check. Therefore, if P of k is true, then P of k plus 1 is true, and therefore our original proof is true, or our original theorem is true. Okay, so there were two more things that we didn't quite get to last class. Now that I'm looking at my notes, I'm going to post these on Google Classroom. I'm going to do a scan, I promised. So you'll see that as well as this lesson video. The two things we were talking about were the division and Euclidean algorithms, which are actually pretty interesting if you want to take a look through it. I don't think it's totally necessary in order to be successful on this test. But one thing that I will want to kind of explicitly go through, I actually have the notes right here, are just these divisibility rules. So right up here you can see the kind of cool way that we actually can use our Euclidean algorithm to get a greatest common divisor. This is how computers do it. So if you were ever wanting to make a program about this, you'd probably use the Euclidean algorithm. But we also know that there's a way to do this there's a way to find the greatest common denominator or the greatest common factor, as well as the least common multiple. So just stepping through this, if you want to find the greatest common factor of two numbers, all you have to do is find the unique prime factorization. Doing this stuff, it really, especially for the test, comes down to really just memorizing certain things. I tend to try to divide by 2 as much as possible with my numbers until I get to a small one, and then kind of manually figure out which other prime numbers divide into it. But there are some examples. There's some great rules for it. I think there's some, like if you have like a 3-digit number and you add it up and it adds up to a certain amount, and it's divisible by that number, and each of the digits are divisible by the number, the number itself is divisible by that number. But again, it's just a lot of memorizing. I kind of just took the L on that one and really grinded through that problem. But if you really want to be 100% on that, there is some good examples on page 55. But I'm just going to go through some of these examples. First one was unique prime factorization. And so you want to find it, and then you want to find the product of the common prime factors. So if we're looking at the greatest common factors of 1,960 and 3,150, you break your 1960 down into your common factors. So 2 cubed times 5 times 7 squared will get you back here. Again, look up here if you need to review that. Do the same thing with 3,150, and what we should start noticing is that at certain values, at certain of these, when you're finding the greatest common factor, you're looking at which factors are common throughout within your primes. So here we'll see we have a factor of 2 from the 3,150. Notice it's just that one. We don't take into account the cube. Right here, this 5 is going to be our greatest common prime factor. And then right here, we have our 7. So 2 times 5 times 7, we multiply all those together, we get 70. The least common multiple is kind of like the opposite. We take our unique prime factorization, which again is like up here, and then we collect the highest degree exponent from each term. So if we're looking at something like what's the least common multiple of 12,375 and 90, we got to break them 390, 390. Then we got to look at each of them, put them down into their prime factors. 12,375 is going to be 3 squared times 5 cubed times 11. 390 is 2 times 3 times 5 times 13. So you take the highest power from each. So we compare the 3's. This one has a 3 squared. We're taking that one. The 5 cubed, we're taking that one. The 11, well, it's not even included in 390, so we're going to take it. And in terms of the 390, 2 is not included in the other number, nor is 13. We take that string of values, multiply them together to get our least common multiple, or the smallest number that both of them fit into. So, yeah, take a look through this video. If you have any questions, please get them written down so that we can go over it during class on Saturday. I hope you guys are having a good week. And yeah, look out for my posts, and I will see you in a few days.